In this video, we will continue our discussion of limiting reagents. At this point, we need to define some terms. The first is the so-called theoretical yield. This is the amount of a product that could be formed based upon the limiting reagent. It's the maximum amount that could be produced from that limiting reagent. In addition, then, we have the idea of an actual yield. This is the amount of that product that you get by actually going in the laboratory and doing the experiment. In many cases, this is not exactly the same as the theoretical yield due to a variety of potential sources of error. In most cases, the actual yield is lower than the theoretical yield. If the actual yield is above the theoretical yield, this usually indicates that there is some sort of contaminant present in the product, and it's usually a determinate error that we could potentially eliminate. So the idea of being able to get a pure product, separating it from the excess reagents that you might have started with. You also sometimes have to ask yourself, did the reaction go to completion? Did I allow the reaction to go long enough? And these are issues that would have to be addressed. So, in the final situation, then, we can combine these two pieces of information to come up with a so-called percent yield. The percent yield is calculated by taking the actual yield and dividing by the theoretical yield to come up with a fraction, which then multiplied by 100 gives you your percentage. And, of course, in an ideal world, percent yield would be 100%. As an example of how to combine the concepts of limiting reagent and percent yield, you might have a question as given here where magnesium can be reacted with elemental oxygen to produce magnesium oxide. If 13.2 grams of magnesium are reacted with 10.2 grams of O2 in a container, what is the theoretical yield of magnesium oxide? Well, first thing we need is a balanced chemical reaction, so this is a relatively straightforward one to balance, and so we have 2 magnesiums and 1 O2 producing 2 MgOs in the solid state. If we then start with the given from the problem in terms of the grams of magnesium, the first thing we should do is try to convert that into moles. We're going to use the atomic mass of magnesium from the periodic table. So we then put the grams of magnesium in the denominator, the moles in the numerator, and that will allow us to cancel the grams of magnesium. At this point, then, we're going to use a stoichiometric ratio between the magnesium and the magnesium oxide from the balanced reaction. So that is 2 to 2. The moles of magnesium will cancel at this stage. And then finally, we can turn this into the grams of magnesium oxide by using the molar mass of MgO, which turns out to be the sum of the atomic mass of magnesium and oxygen. So essentially 24.3 plus 16. And you'll see that at this stage, the moles of magnesium would cancel. And we can then do our math and come up with a value of 21.88, noticing that there should be 3 significant figures, and so rounding to 21.9 grams of MgO. If we then do a similar calculation starting with the oxygen, first convert that into moles, so dividing by the molar mass of O2, which is approximately 32, multiply by the ratio of the magnesium oxide to O2 from the balanced reaction. We see that we have a 2-to-1 ratio there. And then again multiplying by the molar mass of the product, which is MgO. In this case then we multiply everything in the numerator and divide by the numbers that are in the denominator. We come up with 25.69, again with 3 significant digits, so 25.7 grams. At this stage, the smaller of these two numbers that we have calculated will be the theoretical yield of magnesium oxide from this reaction. It also then indicates that the magnesium metal was the limiting reagent and that the O2 was in excess. So we can take this a step further and calculate our percent yield. If 19.2 grams of the magnesium oxide is collected from doing the reaction, the question becomes what is the percent yield for this chemical reaction. And remember that the formula for percent yield is the actual yield divided by the theoretical yield times 100. In this case, then, the actual yield is the 19.2, the 21.9 or 21.88 grams of MgO from our calculation is the so-called theoretical yield, and we then plug that into our equation and get a value which turns out to be 87.751%. We then have to round that to 3 significant digits, so 87.8 is our final answer. And finally, we can consider the various kinds of reactions that you might encounter where you may have to do these kinds of calculations. The first kind of reaction that is very common are combustion reactions. Combustion reactions oftentimes involve an organic fuel reacting with oxygen, quite often excess oxygen if it's done in air. And so the first reaction here is a reaction of ethanol with elemental oxygen to produce carbon dioxide and water. The only products are CO2 and water. And balancing this reaction is a little bit tricky because you need to take into account the oxygen that is actually in the ethanol in addition to the O2. But always in a complete combustion reaction involving an organic compound, the products are going to be CO2 and water. A second example here is taking an element such as elemental carbon and reacting with oxygen. This is a simpler reaction. The only product in this case is carbon dioxide because there's no hydrogen present in the fuel. So this is approximately the same as burning coal. Another example might be taking the element sulfur. Yellow sulfur is typically formulated as a molecular unit of S8. This also will react with elemental oxygen to produce sulfur dioxide, which is a potential pollutant as part of air pollution. And then finally, elemental hydrogen, which we've talked about a few times now. Another very commonly encountered reaction is the fact that metals will react with nonmetals, and so alkali metals are a great example. The alkali metals are in group 1A. They have one electron in their valence shell, which happens to occupy the S-type orbital. These are fairly readily lost to form 1+ ions. And so, for example, if we were to take a metal from the alkali group and react it with the elements that are in group 7A, these are the halogens. These are all diatomic elements. So the overall reaction would be based on what you see here, where the product would be a formula of Mx, where M is the alkali metal cation and X is the halogen anion, with the metal being 1 plus and the halogen being 1 minus. The balanced reaction is relatively simple. A specific example would be reaction of potassium metal with fluorine to produce 2 potassium fluorides, which the ionic compound potassium fluoride is typically a solid at room temperature. The alkali metals also vigorously react with water. As shown here, the products of this sodium hydroxide are soluble in the water, so whenever an ionic compound is dissolved in water, we break it apart into the ions, and so you end up with producing sodium ions in aqueous solution along with hydroxide ions. And then the other product is the hydrogen. This reaction produces quite a lot of heat, and if there's enough heat produced, the hydrogen can combust, and we have a further reaction that we have discussed previously. It turns out that the halogens are 1 electron short of having a noble gas configuration, so they quite often react very vigorously with metals to produce the negatively charged anions. And so in this particular case then, some examples: reacting halogens with metals oftentimes produce metal halides, where there might be some number of halogens that are acting as the negative ions, and the metal having some positive charge associated with that particular element. The example shown here is vanadium metal reacting with fluorine. Vanadium's highest positive charge is 5 plus, so hence we produce the vanadium 5 fluoride as a solid. Halogens also react with elemental hydrogen to form the hydrohalic acids in the gas phase, or the hydrogen halides, and this is a pretty common type of reaction that you might encounter as well.